Hello everybody. In this video I am going to talk about length contraction in special relativity. We know that length contraction is one of the very important consequences of the postulates of special theory of relativity proposed by Albert Einstein. What is length contraction? Length contraction is that effect by which objects appear to have shorter lengths to observers in relative motion. Let us take an example and discuss this further. Suppose there is an earth-based observer. Let's call him O. Now, if this observer on earth carries an object, let's say of length L0, if an identical object having the same length is carried, let us say aboard a spaceship by another observer O prime, now the length of the object as measured by this observer O prime is going to be again L0 because it is an identical object, but the earth-based observer O measures the length of this object to be shorter than its actual length. Now this is because the spaceship is moving with a velocity v, let us say, with respect to the earth-based observer O. Therefore, these two are two different frames of reference. That is, these two observers are in different frames of reference, and these two inertial frames of reference are in relative motion with respect to each other, and therefore any length measured by the earth-based observer for this object which is in relative motion will appear shorter. Now, what is a simple expression that gives the contracted length? The contracted length L is equal to the proper length L0 multiplied by 1 minus v squared over c squared. Now this length we know is called as the proper length as measured by the observer who is at rest with respect to that object, whereas this observer is in relative motion. So from the perspective of the observer O prime, Earth is appearing to go with the same velocity in the opposite direction, right? So this is the simple expression that gives us this, and we know that in special relativity this particular expression appears in several equations, and therefore it has a name called Lorentz factor gamma, which is given by 1 over square root of 1 minus v squared over c squared, and therefore we can write again length contraction L as L0 over gamma. Now we know that the velocity of any object is going to be always less than or equal to the velocity of light, and therefore this particular term is always going to be less than 1. So square root of 1 minus v squared over c squared is always going to be less than 1, and therefore our L is always going to be less than L0, and therefore we can call this length as the contracted length. Right. Now there may be a question, what about this observer if he tries to measure any length on Earth? Obviously this is also in relative motion with respect to this observer, and therefore all lengths will appear to be shorter to this observer. Suppose he has a means to measure the diameter of the Earth, let us say the proper diameter of the Earth as measured by the Earth-based observer is d0. Now the observer in the spaceship would measure this d to be contracted, so he will measure d is equal to d0 multiplied by square root of 1 minus v squared over c squared. So the Earth would appear to him to have a contracted length in a particular direction parallel to which he is moving. So please remember the length contraction can occur in the direction of motion only. So if the direction of motion is this way, the spaceship would appear contracted. So if the proper length of the spaceship is S0, the earth-based observer would measure the length of that spaceship also to have contracted. So S is the length, contracted length of the spaceship. The proper length again multiplied by the same factor 1 minus v squared over c squared. So any other length measured by the observer in the spaceship, that is observer O prime in the spaceship on Earth, would also appear to him to have shortened. So this scale, this object, for example, any object it could be, this object as measured by this observer would have a length L is equal to L naught 1 minus v squared over c squared, same factor. So we can clearly understand therefore that two observers in relative motion will measure lengths carried by each other to have contracted. So therefore clearly one can conclude that length contraction, just like time dilation, is a reciprocal effect. So any object in his own frame of reference, the observer would have to measure a length called proper length, and in other frame of reference, if the object is in relative motion with respect to himself, he would measure that length to be contracted length, given by this particular expression L is equal to L naught multiplied by 1 minus v squared over c squared within the square root. Okay, so this is the expression for length contraction. One can clearly see that the contracted length would depend on v. So that is the velocity, velocity of the object in relative motion. So as the velocity increases, the contracted length is going to become more and more contracted. All right. So as v increases, L further decreases. So for velocities closer to the speed of light, the object would almost appear to have no extension in that particular direction in which it is moving. So one can clearly see, for example, if we have a book, for example, we carry a book whose let's say the length is L naught and the height is, let's say, h naught, and if the book is moving in this particular direction at a velocity, let's say, close to the speed of light, let's say about 0.8 c. Now an observer on Earth would measure this length to have substantially contracted. This L naught should have substantially contracted, as L of course is equal to L naught times 1 minus square root of 1 minus v squared over c squared, whereas this one would remain unchanged. This is a very important point that one has to know, because the direction of motion is parallel to the direction in which the contraction occurs, right? So if it is 0.8 c, how much would be the contraction? The L would be about L naught times 1 minus 0.64, 0.8 squared c squared, c squared, so it would be 0.36, 0.6, so it is about 0.6 times the original length of the book. This would be the contracted length. So about 60% is the remaining length. So the object would appear to be about 60% as long as it originally was if it were traveling at a velocity of 0.8 times, that is 80% of the speed of light, where speed of light we know is 3 into 10 power 8 meters per second. It's taken to be roughly equal to this value, right? Now the question would be, are there any proofs for the length contraction? Yes, there are several ways in which one can provide proof for length contraction. One of the very interesting proofs for length contraction is what is called as the Nuan lifetime paradox. What is this Nuan lifetime paradox? We know that muons are subatomic particles whose mass is 207 times the mass of the electron. So the muon mass is 207 times the mass of the electron, and the muon charge is same as the electric charge of the electron. So muons we know are of two types. That could be muon plus, it will have plus E charge, and the muon minus, mu minus will have minus E charge. So these particles are unstable particles which decay into again positron or electron, depending upon whether originally it was mu plus or mu minus that was there. So the symbol for muon is mu. Use the symbol mu for the muon. Right now, so it's not a very massive particle, it's 207 times the mass of the electron, but its mass is less compared to, for example, proton or neutron. Right now, these are unstable particles and they decay. Now, how can one explain the decay of muons? That is, the time it takes for a particle, subatomic particle, to decay into other particles is called as the lifetime of that particular particle. So here when we say muon lifetime paradox, where is the paradox? These muons have a very short lifetime of about only 2.2 microseconds. The muons decay only in 2.2 microseconds. Microsecond is, we know that it is 2.2 into 10 power minus 6 seconds. So in such a short span of life, the muons are able to travel a vast distance from the upper atmosphere to the surface of the earth. So at the sea level, the number of muons detected are too many, way too many to be explained with this short lifetime. How many muons are detected? Roughly about 1 muon is detected every centimeter square per minute on the surface of the earth. In order for these many muons to reach the surface of the earth from the upper atmosphere, from about 6.6 kilometer, let's say, where they are actually created because of collision of cosmic ray particles with molecules in the upper atmosphere, these muons are actually created. After creation, in about 2.2 microseconds they have to decay, but they are able to reach the sea level without getting decayed, and this can happen only based on explanation of this muon lifetime paradox using length contraction as well as time dilation. I am not going to elaborate this further. A separate video is being posted to explain this muon lifetime paradox in greater detail. Please do check that video. Right. What about this expression? Is there a way to derive this expression? Yes, there are a few methods by which we can derive this expression. The derivation is similar to the derivation that we have done for the time dilation. So I'm not going to do that derivation in this particular video. I'm going to post a separate video for the derivation of the length contraction expression. Please do check out that video as well. So length contraction is one of the very important effects of special theory of relativity. Thank you.